Logs and exponents are a big part of calculus. We wouldn't be able to do without them, particularly the natural logs and the base e to the x. It's a link between many functions in calculus. That being the case, we cover natural logs and exponents, particularly the base e, in AdMaths. In the algebra syllabus, we introduce the natural logs, and we also do basic functions with them. And then there are questions on the log and exponential graphs and deductions from them. There's the basic exponential graph. You'll notice cutting it y equals 1, cutting the y-axis, and cutting the x-axis at 1 for the log graph. A bit about them. A reminder that these are inverse functions. We have dealt with that earlier. And so with an inverse function, what happens is the one reverses the process of the other one. So for example, if f of m is equal to n, then f minus 1, the inverse function, f minus 1 of n, will be equal to m. So you'll notice m goes to n, and then this takes n back to m. And it's just a case of swapping the x and y. If we plot 2 points where the x and y are swapped, so we have 5, 1, and then I've swapped the x and y to get 1, 5, you'll notice that in fact they reflect through this line y equals x. This is the same distance out vertically from the line as that one is out that way. So all functions of the inverses are reflections of one another about the line y equals x. Let's do example 10 from page 110 in your textbook. Notice that these here are links. If you use the PowerPoint, this is directly from the PowerPoint. If you click that link, you'll find you will actually go into the Mindborn. I'm not going to worry about it too much now, but that link too, you will go into the Mindborn as well. You'll notice I still have to log in there, but once you've logged in, it'll still take you to the link that you've been given. So we have the function 2e to the x minus 1 minus 1. So this is a function of e to the x, but with various adaptations. Find the value of f of 1. This question is just leading you into it. We need that point where f of 1, where x is 1 later. And of course, to find the value of f of 1, we just substitute the value of 1 for x. So there's 1 there. Solving, we get y equal to 1. So f of 1 equals 1. Let's put it there for now. So now we're going to be sketching the graph, this very graph here. We have to plot the intercepts with the xy axis, the horizontal asymptote, and that point. The x-intercept occurs when y is 0, which means f of x is 0. To solve this for x, we first need to solve for e to the x minus 1. Now to go any further, we need to try to get that x out of the exponent. The only way to do that is to use logarithms. So we're going to go to logarithmic form. E is the base. So e will be the base of the log, which means it will be ln There's the number, so we're taking log of the number, and that's what it's equal to because the log is an exponent. Now we need to solve for x. Using a calculator, we get approximately 0.3. The y-intercept, x is 0, and we substitute 0 for x now. And we end up with approximately negative 0.3. Now we're going on to the asymptote, the horizontal asymptote, and there you can do this by reasoning if you know your basic y equals e to the x graph. Y equals e to the x is asymptotic to the x-axis. The horizontal asymptote of y equals anything a to the something is, and there it is, y equals 0, the x-axis. So now, if we subtract the 1, there's the minus 1, that moves the graph down 1. So that's what we're going to do. So instead of y equals 0, we're going to have y equals minus 1. So there it is. We need to plot that point 1, f of 1. We have already done the working, so there we are. It's the point 1, 1. So now we have 3 points on the graph. We know the graph is asymptotic to this one here. Well, if it's coming in this direction, it has to be asymptotic in the direction to the left, to the negative side. So we can sketch a curve passing through these 3 points and going asymptotic. Now we have to find the equation of the inverse function f minus 1. So remember that if we have to find the equation of an inverse, we need to swap the x and y. So we're going to take f minus 1 of x. We're going to find f minus 1 of x by taking this as y equals. There we are. That's that equation with y equals. Now we're going to swap the x and y. And we're going to solve for y. Same process. We're first going to solve for e to the y minus 1. Go to log form and solve for y. Now we need to go to log form to get that y out of the exponent. And we can solve for the y. So there y equals that. So therefore, there is our inverse function. To show that two graphs intersect at a point, all we have to do is show that they both lie or pass through that point. And if they both pass through that point, they must intersect. Now, we already know that f of x passes through that point because we've just used it in the graph. There it is there. So all we have to show is the inverse function passes through that point. So let's substitute x equals 1 into the inverse function. So there we are. I've taken the inverse function and I'm substituting 1 for x. And then we make the statement that f minus 1 passes through it as well. course, that means that f and f minus 1 intersect at 1, 1. Now we have to sketch the graph of f minus 1 of x. Easiest way to draw the inverse of a function when you already have the graph of the function is to use that symmetry about the line y equals x. Plotted by substituting, by swapping the x's and y's. So there we are. The original graph has an asymptote of y equals minus 1. Therefore, the new graph will have x equals minus 1. 0.3 x-intercept will become 0.3 y-intercept. Negative 0.3 y-intercept will become 0.3 x-intercept. And there is our new graph. Asymptotic to the negative side, so therefore this one's going to be asymptotic to the negative side of y. Domain and range of both graphs. The domain is how far left and right a graph goes. Well, if you have a look at the red graph, the exponential graph, while it's going upwards there steeper and steeper, it always goes out still to infinity. So it's coming from infinity, negative infinity to infinity. So there's negative infinity to infinity. The range, the vertical range, well, it can't go below negative 1. It can't be equal to negative 1, so it's from negative 1, not including it, to infinity. You can use either notation. That's the easier notation to use there. But of course here, that's the easiest notation to use. Interval notation is usually the easiest and quite acceptable. But if there is a shorter notation, use it certainly. Now, the inverse function, all we have to do is do that swap. We can reason once again with the blue graph, but why don't we just say, well, the range of the inverse will be the domain of the original function with a y element of r. The domain of the inverse will be the range of the function with an x. So there we are. Notice those two drawn in the same color, so you can see y element of that, and this is x element of that. Y element of reals, x element of reals, y element of reals. So determine graphically where values of x for which f of x is less than f minus 1 of x. And it's positive values of x. So we don't have to worry about anything on the left-hand side of the y-axis at all. So this says wherever the red graph, which is f of x, is below the blue graph, f minus 1 of x. There we go. It's below the whole way to there, but we're limited to positive values of x only. So it's from there to there. It's less than, so it doesn't include the endpoints. So therefore we'll have the round brackets for the interval notation. Values of x for which f minus 1 of x is greater than or equal to minus 1. Well, that means that the blue graph, f minus 1 of x, must be above the line y equals minus 1. Notice the inverse graph, so the blue graph must be above the line y equals minus 1. So there we are, y equals minus 1 is its asymptote anyway. So from there, includes that because it's all equal to, and it does cross the asymptote line, and it goes forever upwards and forever to the right. So therefore, approximating, that's about negative 0.7, including with a square bracket, and it goes to infinity. So now we have exercise 6, question 2, it's question 2A, on page 119 of the textbook. That's saying pause and try this one yourself before going on to the solution. The solution does follow. This also, this one doesn't. I thought this, it does have it, sorry. There we are, it does have it in fact. You can refer to the mind board in the same way by clicking that one there. All right, so pause it, try it yourself as far as possible. It does go through in steps, so what you can do is you can try it, and it has hints along the way if you want to, if you can't do it totally on your own. So let's have a look at the first part. Sketch that graph. Plot the intercepts of the axes and the horizontal axis, asymptote. Notice you are following very much the same sort of thing as the previous question, as the example. So we're going to find the x-intercepts by putting y equal to 0. So we'll have f of x 0. We're going to solve for e to the x. Pause along here if you then want to do each step along the way. And I've gone straight to the answer. It's a pretty straightforward system. Solve for x. Remember, all you have to do is e to the naught is 1. So therefore x equals 0. The y-intercept, x is 0. We're now going to put 0 for f of x. 0 for x, I mean. So f of 0. Pretty straightforward. 0. You'll probably be able to see that it's going to be, because if the x-intercept is 0, the y is going to be. This means we're going to have to find another point somewhere. Horizontal asymptote. Well, we can do this by reasoning as well. Same reasoning as example 10. E to the x has an asymptote. Y equals e to the x has an asymptote of the x-axis, y equals 0, and this is plus 3. So therefore your asymptote is going to be y equals 3. We need to plot another point. Let's do x equals 1. So I've substituted 1 for x and solved for y, approximately equal to negative 5, 2. And there's the point. So we can now plot our graph. Clearly, it's got to go through there. It's got to go through there. Well, it's moving to the left then, so it's got to go to the left, asymptotic. Question 2. Find the inverse function. Remember that swapping the x and y. So we write it as y equals first. Now to solve, we're going to solve for e to the x and then for x in order to find, e to the y and then y. Because once we swap it for our inverse function, now we're going to solve for e to the y. And at that stage, we're going to have to go logarithmic form. Notice the e hasn't disappeared. Ln means log to base e. We have y equals that of the swapped for after the swap, so therefore there's our inverse function. So now we're going to draw the graph on the same set of axes, and remember we can use symmetry about the line y equals x. So there are the swaps. The original asymptote goes to x equals 3. That point goes to negative 1.521. And of course that stays the same. So now we have a point there, and the asymptote. Domain and range of the graphs. It's the same as last time. So there's our domain. You can check your answer. There's the range, and of course notice that the domain and range of f is related to the domain of the inverse, where the x has been replaced as y, and that domain goes to the range of the inverse function with y. So this again is positive values of x for which f of x is less than or equal to f minus 1 of x. So the red graph must be below or equal to the other graph. Now, here's the thing. Lots of people automatically see this as being forever down here. But don't forget, this is an asymptote. So this green graph, the inverse, isn't going further than x equals 3. But this red graph is going outwards forever, even though it doesn't seem to. So it appears that f is below f minus 1 for x greater than or equal to 0. A big but. Consider the domains. That's what I was talking about here. Consider the fact that f minus 1 stops at 3, but f goes to infinity. So f is going to cross f minus 1 again at some stage. Let's pull down an exaggerated version of it, and you'll see that. Here I've gone to a smaller scale, and you'll see that way down here, and this is drawn on order graph, you'll see way down here somewhere, just below -50, the F graph crosses the F-1 graph again. So we'll say at approximately 3, x value of 3. Notice we could argue and say, but this graph here isn't at 3, the function isn't at 3, but it's pretty well as close as you can get to 3 at that stage. It's getting closer and closer. So it's fine if we do approximate 3. So therefore, we're going to say that x is the element of 0, because it includes, because it's or equal to, and then 3, where it becomes larger than the inverse again. So now we need f of x to be bigger than or equal to 1. The red graph to be bigger than or equal to 1. So that's the line y equals 1. So the f of x, the red graph, must be above or equal to the line y equals 1. So there we go. There's the section of the graph which is above that line. Notice we're including that point because it says or equal to. Now we're going to have to find the value of that point, the x value of that point. I'm approximating it there, which you can go, if it tells you to do it graphically. Otherwise, you're going to have to solve for f of x for that -3 to the x, e to the x plus 3 equaling 1. If you haven't managed this one on your own totally, it might be worth leaving it a day and then going through and trying this question again.